let A be an 3 by 3 matrix over R, be such that A raised to 8 raised to 8 is equal to identity matrix. Then options 1. Minimal polynomial of A can only be of degree 2. Second option, minimal polynomial of A can only be of degree 3. Third, either A equal to identity matrix or A equal to minus negative of identity matrix. And fourth option is there are uncountably many A satisfying the above. Now here given A is a 3 by 3 matrix, and the condition given is A raised to 8 is equal to I. Now what we will do, if A is equal to I 3 by 3 matrix, then we know that characteristic polynomial is of AI is lambda minus 1 all cube, because this is. Now what is minimal polynomial? Minimal polynomial is the lowest degree polynomial such that that satisfies A. So if A equal to I, then minimal polynomial is lambda minus I. So from here, the degree of the minimal polynomial of identity matrix is 1. So what we can do, we can cancel out. First option is not true, second option is not true. And what about 3 and 4? Okay, so now what we will do is, third option is either A equal to 3 identity or minus identity. Now if I take A equal to 1 0 0 0 minus 1 0 0 0 1, this is not equal to identity matrix, and also not equal to minus of identity matrix. Then what about A square? Here this is diagonal matrix, so 1, A square is 1 0 0 0, minus 1 becomes minus 1 square 0 0 0 1. This is equal to I. So which implies A raised to 8 is equal to I. A square equal to I, then A raised to 8. So third option is also false. This option is also false. So only one option is there. This is a C-part question and 3 options are false. This is the correct answer. Now how to get, that means there are uncountably many A satisfying this condition. For that, if I choose A equal to some 1 0 A 0 1 0 0 0 minus 1, where A belongs to R, then A square is equal to what you will get, the product of these matrix 1 0 A. This will becomes A minus A. So I will get this like 0 0 0 1 0 0 0 1. So A square is equal to identity, therefore A raised to 8 is equal to identity. So A is any number in real number, A be any real number, so this is uncountable. So option 4 is true. The question is trace of the matrix, and matrix is given 2 1 0 0 2 0 0, 0, 3 all raised to 20. So we want to find out the trace of this matrix. Here matrix is triangular, okay, because this is an upper triangular matrix. Therefore eigenvalues of matrix are diagonal entries. So what will be the diagonal entries? If I take A equal to 1, 2, 1, 0, 0, 2, 0, 0, 0, 3. So this is A. Then A raised to 20 is equal to this matrix. So eigenvalues of A are therefore 2, 2, 3, because this is an upper triangular matrix. Eigenvalues of an upper triangular matrix are diagonal entries. Now, what will be eigenvalues of A raised to 20? If A has eigenvalue 2, 2, 3, then A raised to 20 has eigenvalue 2 raised to 20, 2 raised to 20, 3 raised to 20. Now we want to find out trace of A raised to 20. So we know trace of A raised to 20 is equal to sum of eigenvalues of A raised to 20. So trace is sum of eigenvalues of A. So this is equal to, what are eigenvalues? 2 raised to 20 plus 2, 2 raised to 20 plus 3 raised to 20. This is equal to 2 into 2 raised to 20 plus 3 raised to 20. So what is trace? This, and option is third option. Option is correct. Next problem. Let A be an n by n matrix where n strictly greater than 1, satisfying A square minus 7A plus 12I is equal to 0, and where I and 0 denote the identity matrix and 0 matrix of order n respectively, then which of the following statements are true? First one is A is invertible. Second one, t square minus 7t plus 12 n is equal to 0, where t is trace of A. And the third one, d square minus 7t plus 12 is equal to 0, where d equal to determinant of A. And the fourth one, lambda square minus 7 lambda plus 12 is equal to 0, where lambda is an eigenvalue of A. So we have given A is an n by n matrix and given that n greater than 1. Okay, now satisfying equation A square minus 7A plus 12I is equal to 0 matrix. So it satisfies this condition. Now if I take this A into A minus 7I plus 12I is equal to 0, I can change this like this. Then A into A minus 7I is equal to minus 12I. If I take determinant on both sides, what is this? Determinant of A into determinant of A minus 7, determinant of A into determinant of A minus 7I. We know that determinant of A into B equal to determinant of A into determinant. This is minus determinant of minus 12I. But we know that determinant of I is 1 and determinant of minus 12y, this cannot be equal to 0. So which implies determinant of a cannot be equal to 0, because the right hand side determinant is not 0, this quantity is not 0, therefore this either of them is not 0. So if determinant of a is not 0, a is invertible. So option 1 is correct. Option 1 is correct. Now what about second option and third and fourth? Now if I take a matrix 3, 0, 0, 4, we know that root of this root of the polynomial lambda square minus 7 lambda plus 12 is equal to 0. Okay, this is corresponding polynomial. So what is the characteristic equation of this a? Here trace is 7 minus 7 lambda and determinant is 12. So by Cayley-Hamilton theorem, what you know that a satisfies its characteristic polynomial. So a square minus 7a plus 12 is equal to 12i is equal to 0. So here our equation, our matrix satisfies this. Now what about the polynomial? What is trace of a? Trace is equal to 7 and the determinant is equal to 12. Now what is its corresponding polynomial? Lambda square minus 7 lambda plus. Now for the third option it is 12n. n is equal to 2 here. So 24. Now check whether this 7 is a root of this polynomial. 7 is a root of this polynomial. Here 7 is not a root of this polynomial. Therefore third option is false, because 7 doesn't satisfy this. Okay, if it satisfies, then 7 must divide 24, but 7 doesn't divide 24. So third option is so second option is incorrect. And what about third option? Third option is d square minus 7d plus 12. That means what is here? Here 12, we have to check whether 12 is a root of this. But here already roots are 3 and 4. So 12 is not a root. Therefore third option is also false. Sorry, here it is second option and here third option is also. Now what about fourth option? Lambda square minus 7 lambda plus 12 equal to 0, where lambda is an eigenvalue of a. Now given a satisfies this this polynomial equation, therefore we know that minimal polynomial of a divides lambda square minus a lambda plus 12. So what are the possibility of minimal polynomial of a? Either it is lambda square 7 lambda plus 12, or it is lambda minus 7 or lambda minus 3. But this is n is greater than 1, therefore minimal polynomial must be this. That means minimal polynomial of a is this equation. Therefore root of minimal polynomial must be an eigenvalue. Root of minimal polynomial is eigenvalue. Therefore 3 and 7 are eigenvalues. So therefore 3 and 7 are eigenvalue. Therefore lambda satisfies this equation. Therefore fourth option is also correct. Thus option 1 and 4 are correct answer. Question is, let Rn n greater than or equal to 2 be equipped with standard inner product. Let set v1, v2, etc. vn be n column vectors forming an orthonormal basis of Rn. Let A be n by n matrix formed by the column vectors v1, v2, etc. vn. Then options are A equal to A inverse, second one A equal to A transpose, third one A inverse equal to A transpose, and fourth one determinant of A equal to 1. So this is a B part question, therefore one answer is correct. Now given set v1, v2, etc. vn are orthonormal vectors, set of orthonormal vectors, which implies, what I mean by orthonormal vectors? Suppose vi dot vj, that must be orthogonal, is equal to 0 for I not equal to j. That means vi dot, if you take any different distinct vectors, their dot product is 0, and vi dot vi must be equal to 1, that is I equal to 1. Okay, now what is A? A is equal to, is a matrix whose columns are these vectors v1, v2, etc. v. So first column is v1, second column is v2, etc. v. Now we want to show that what about its transpose and determinant. So if I take A transpose, what will be the transpose of A? So A transpose will be, v1 is here column, and then that column becomes row, v1, next v2 is second row, v3, etc. vn be the. Now what is A dot A transpose? A into A transpose is equal to, if I dot product this first column, or A transpose A, this is first row into first column, v1 dot v2. So that means v1 b1 1, and if you choose what about the other values, 1, this is matrix 1 0 0 0, and what about v2 dot v2 is this is 0 1 0 0, etc. you will get 1. That means if you multiply this by this by this, then the first element v1 is equal to 1, and all other elements are v1 dot v2 v3, etc. So this is an identity matrix. So A transpose A is equal to identity, which implies A transpose equal to A inverse. So this is the correct answer. So only option 1 is correct. So we got A transpose equal to A inverse. There is an option 1 is correct, and A transpose A is equal to I doesn't implies A equal to A transpose. So option 2 is not correct. And what about option 1? Option 1 is not correct. A may not be a symmetric matrix. And fourth one, determinant of A equal to 1. But here A transpose determinant equal to 1. Determinant of A transpose determinant of A equal to 1. We know that determinant of A transpose is determinant of A is square equal to 1, which implies determinant of A is plus or minus 1. This is not equal to exactly 1. So this option is correct. Only option 3 is correct. This E to V is a linear transformation with only one has eigenvalue. Then which of the following must be true? First option, t equal to I, t minus I equal to 0. Second option, t minus I all raised to n minus 1 is equal to 0. T minus I all raised to n is equal to 0. T minus I all raised to 2n is equal to 0. Now here given t is equal t from V to V is a linear transformation with 1 is the only eigenvalue. So now the corresponding matrix is this is dimension n, so is an n by n matrix with all eigenvalues are 1. We know that identity matrix I n by n has all eigenvalues 1. Then option 1, 2, 3 and 4 are true, but this is not the only case. If I choose for n equal to 2, a 2 by 2 matrix A22 is equal to 1, 1, 0, 1. So this is a triangular matrix. So eigenvalues are 1, 1. That is diagonal entries. So all eigenvalues of this matrix is 1 and n equal to 2 here. N equal to 2 here. Now I am taking instead of t I am taking A. There. A minus I matrix is 0, 0, 1, 0. So here all eigenvalues are 0. So now this is not equal to 0, right? A minus I or t minus I equivalent to t minus I is not equal to 0. Now I am taking second option, t minus I all raised to n minus 1, which is equal to a minus I all raised to n. N is 2. 2 minus I. That is a minus I itself. But here a minus I not equal to 0. Now next option is a minus I or t minus I all raised to n minus or all raised to n, which is equal to a square. If you multiply this, you will get 0. If a minus I all raised to n is equal to 0, then a minus I all raised to 2n is equal to 0. So option from here, option 1 is, what about options? Option 1 is t minus I equal to 0. That means a minus I equal to 0. That is false. And option 2 is t minus n minus 1. That is not equal to 0. So second option is also false. And what about 3 and 4? So from the example it is true. But how to conclude that? So for a minus I. Here, this is a all eigenvalues are we know that all eigenvalues of A is equal to A are 1. Then what will be all eigenvalues of A minus I, which is equal to 1 minus 1, 1, 0, which is equal to all eigenvalues of A are 0. If all eigenvalues of A are 0, then A is nilpotent. Nilpotent. What do you mean by nilpotent? A raised to some k is equal to 0 matrix. So all eigenvalues of A minus I are 0. So A minus I is nilpotent. That means A minus I all raised to some k is equal to 0 for k less than n. So here we will get T minus I all raised to k equal to 0. Therefore k less than 1. Therefore option 3, option 4 are correct answer. A, B and 3 by 3 matrix or R B such that A raised to 8 is equal to identity matrix. Then options 1, minimal polynomial of A can only be of degree 2. Second option, minimal polynomial of A can only be of degree 3. Third, either A equal to identity matrix or A equal to minus negative of identity matrix. And fourth option is there are uncountably many A satisfying the above. Now here given A is a 3 by 3 matrix, and the condition given is A raised to 8 is equal to I. Now what we will do, if A is equal to I 3 by 3 matrix, then we know that characteristic polynomial is of AI is lambda minus 1 all cube, because this is. Now what is minimal polynomial? Minimal polynomial is the lowest degree polynomial such that that satisfies A. So if A equal to I, then minimal polynomial is lambda minus I. So from here the degree of the minimal polynomial of identity matrix is 1. So what we can do, we can cancel out. The first option is not true, second option is not true. And what about 3 and 4? Okay, so now what we will do is, third option is either A equal to 3 identity or minus identity. Now if I take A equal to 1, 0, 0, 0, minus 1, 0, 0, 0, 1. This is not equal to identity matrix, and also not equal to minus of identity matrix. Then what about A square? Here this is diagonal matrix, so 1, A square is 1, 0, 0, 0, minus 1 becomes minus 1 square, 0, 0, 0, 1. This is equal to I. So which implies A raised to 8 is equal to I. A square equal to I, then A raised to 8. So third option is also false. This option is also false. So only one option is there. This is a C-part question and 3 options are false. This is the correct answer. Now how to get, that means there are uncountably many A satisfying this condition. For that if I choose A equal to some 1, 0, A, 0, 1, 0, 0, 0, minus 1, where A belongs to R. Then A square is equal to, what you will get? The product of these matrix 1, 0, A. This will become A minus A. So I will get this like 0, 0, 0, 1, 0, 0, 0, 1. So A square is equal to identity. Therefore, A raised to 8 is equal to identity. So A is any number in real number. A be any real number. So this is uncountable. So option 4 is true. The problem is, if A is a 5 by 5 matrix and the dimension of the solution space of Ax is equal to 0 is at least 2, then option number 1, rank of A square less than or equal to 3, rank of A square greater than or equal to 3, rank of A square is equal to 3, and fourth option is determinant of A square is equal to 0. Now here given A is a 5 by 5 matrix and given dimension of solution space of A is equal to 2. What do you mean by solution space? It is called the null space of A is equal to, is called a solution. Then dimension of null space of A is equal to 2, and this is called the nullity. So nullity is equal to 2 given. Now very important theorem, we know that theorem, rank nullity theorem. What is rank nullity theorem? Rank of A plus nullity of A is equal to n, which is number of columns of A. Now here, what is we can get rank of A. So we will find out what is rank of A. Rank of A plus nullity. Nullity is 2, which is equal to number of columns is 5. So rank of A is equal to 3. Now what you, if A and B are two matrix, then what do you mean by rank of AB? This is always less than or equal to rank of A and always less than or equal to rank of B. So which implies, what you meant by rank of A square, this is always less than or equal to rank of A. This is less than or equal to 3. We know that rank of A is 3. Rank of A is 3. Now what are the options? First one, rank of A is equal to 3. Second one, less than or equal to 3. Second one is rank of A square greater than or equal to 3. That is 4. Third one, rank of A square exactly equal to 3. That is not possible. There may be matrix which is has rank less than 3. So this is also false. This is correct. Now what about rank of determinant of A square. Now here rank of A is 3, which is less than 5. Therefore, determinant of A is equal to 0. If determinant of A is equal to 0, then determinant of A square is equal to determinant of A into determinant of A, which is equal to 0. So fourth option is also correct. Therefore, 1 and 4 are correct answers. Question is, if A is 2 by 2 matrix, then with over R, then condition given is determinant of A plus I is equal to 1 plus determinant of A. So this is the condition given. Then we can conclude that options are determinant of A equal to 0, to A equal to 0, trace of A is equal to 0, and A is non-singular. So now first let lambda 1, lambda 2 be eigenvalues of A. Then what will be the eigenvalues of A plus I? A plus I is equal to lambda 1 plus 1 and lambda 2 plus 1. Now if we put this, therefore we know that determinant of A is equal to product of eigenvalues. That is the theorem, we know that. Therefore, if we put this condition, determinant of A plus I is, this is 1. 1 implies lambda 1 plus 1 into lambda 2 plus 1. This is equal to 1 plus, what will be determinant of A? Lambda 1 and lambda 2 are the eigenvalues, lambda 1. Now from here, lambda 1 into lambda 2, if you multiply this, you will get lambda 1 plus lambda 2 plus 1 is equal to lambda 1 plus lambda 1 into lambda 2. Which implies from here, we will get lambda 1 plus lambda 2 is equal to 0. Which implies this is sum of eigenvalues. That is, trace of A is equal to 0. So option 3 is correct. Or if we don't know these things, we can choose, we can use trial and error method. If you choose A equal to 0 matrix, then it satisfies this condition. Okay, so we can cancel out option 4. And also if we choose A equal to minus 1, 0, 0, 1, this will also satisfies question number 1, because here A plus I is equal to minus 1, 0, 0, 0, 2. So determinant of A plus I is equal to, this determinant of this matrix is 0. Similarly, 1 plus determinant of A, 1 plus determinant of A is product. This is a diagonal matrix, therefore it's 1 into 1 minus 1 0. So this satisfies both conditions, but a is not equal to 0. So option 2 is not correct, and also determinant of a not equal to 0. Option 3 1 is also not correct. Thus option 3 is correct. Given that there are real constants a, b, c, d such that the identity lambda x square plus 2xy plus y square is equal to ax plus by all square plus cx plus dy all square holds for all xy belongs to R. This implies first option is lambda equal to 5, second option is lambda greater than or equal to 2, third option is 0 less than lambda less than 1, and fourth option is there is no such lambda equal to R. Now here given a, b, c, d, there is no condition for this a, b, c, d, right? We can choose any a, b, c, d such that lambda x square plus 2xy plus y square is equal to ax plus by all square plus cx plus dy all square. Now for this question, now here look at here, lambda x square plus 2xy plus y square. So something, this is like this is something x square plus y, 2xy plus y square. So this is something like x plus y all square, right? So what I am choosing is, I am choosing lambda equal to 1. Then what will happen? I am calling this equation number 1. 1 implies x square plus 2xy plus y square. Now this can be written as x plus y all square. So this is actually is equal to 1 into x plus 1 into y all square plus 0 into x plus 0 into y all square. And this holds for every x, y belongs to R. So this is true for lambda equal to 1. This condition is true for all x, y belongs to R. For here a equal to 1, b equal to 1, c equal to d 0, d equal to 0. So for lambda equal to 1, this is true for all x. Now look at the option. Option 1 is lambda equal to minus 5. So this condition implies lambda equal to minus 1. But for lambda equal to 1, we got the answer. So first option is false. Second option is lambda greater than or equal to 1. So here lambda is included. So now I am looking third option. Here 0 less than, lambda less than 1. Now here there is no 1. So this option is also false. So this option false, this option also wrong. And fourth one, there is no such lambda, but lambda equal to 1. So the correct answer is lambda equal greater than or equal to 1. That is the correct answer. Is let A be an n by n matrix and B be an n by n matrix over real numbers with m less than n. Then options AB is always singular, AB is always first one AB is always non-singular, second one AB is always singular, BA is always non-singular, BA is always singular. And this is also an easy question. So first we give one. A is an m by n matrix and B is an n by m matrix. And also given, what is given? M is less than n. This is very important. Okay. Now what about AB? A is m by n matrix, B is n by n matrix, then AB is m by m matrix. Okay. And what about BA? B is n by m matrix and A is m by n matrix, then BA is n by n matrix. Okay. Now since so we have A and B are matrix m by n matrix and B is n by n matrix. Therefore, we know that rank of A is always less than or equal to m less than n. So m, and rank of B is always less than or equal to m. Also, we know that if rank of A and rank of B are less than or equal to m, then we know that rank of AB is less than or equal to m and rank of BA is also less than or equal to m. Because if A less than m, rank of A less than m, rank of AB less than m, then their product must be, rank of their product must be less than or equal to that quantity. Now here AB is m by n matrix, then AB may have rank m. So we cannot conclude anything. This m by n matrix may be invertible or non-singular. What about here? Rank of BA is less than or equal to m, which is strictly less than n. What is the order of BA? N by n. So rank of BA is less than, n, which implies BA is singular. So what we can conclude? The matrix BA is singular. So option 4 is correct. Okay. Here question is, the system of equations 1 into x plus 2 into x square plus 3xy plus 0 into y equal to 6, 2x plus x square plus 3xy plus y equal to 5, x minus x square plus 0xy plus y equal to 7. And solutions options are, has solutions in rational numbers, has solutions in real numbers, has solutions in complex numbers, has no solution. So this is a system of non-linear equations. So we already know that how to solve system of linear equations, but here is non-linear equations. So we want to do some tricks, because all question in B part, this is a B part section question, so all questions must be, we want to solve it within minutes. So I'm writing what are the equations. First one is x plus 2x square plus 3xy is equal to 6. This is our first question. Second question is 2x plus x square plus 3xy plus 1 is equal to 5. And third question is x minus x square plus y is equal to 7. This is equation number 2. Question number 3. Now look at this question. Here there is x and 2x. 2x square, x square, x square. So what I will do is, I'm adding equation number 1 minus equation number 2 plus equation number 3. Which implies, so what I will do is, I'm subtracting this and adding both. Okay. So from here what I will get, so this implies from here x minus 2x plus x 0, 2x square minus x square minus x square again 0 plus 3xy minus x 3xy again 0, and here there is 0 minus y plus y again 0. This is equal to 6 minus 5 1 plus 7 8. So which implies I get 0 equal to 8, which is an absurd. Okay, so what we can conclude is it has no solution, because it has no solution. So because we have get 0 equal to 8, therefore option number 4 is correct. Option 4 is correct. The problem is, let A be a 6 by 6 matrix over R with the characteristic polynomial x minus 3 all square into x minus 2 all raised to 4, and with minimal polynomial x minus 3 into x minus 2 all square. Then the Jordan canonical form can be, we have given 4 matrices. Now here given characteristic polynomial is x minus 3 all square into x minus 2 all raised to 4, and minimal polynomial is x minus 3 into x minus 2 all raised to 2. Now we can characterize the Jordan canonical form of the matrix. So this is not a diagonalizable matrix because the minimal polynomial does in splits. Now what are the eigenvalues? Eigenvalues are 3 and 2, and 3 repeats 2 times and 2 repeats 4 times. So these are the all eigenvalues. Now what is the degree of each factor of x minus 3? Degree of minimal polynomial has degree. So eigenvalues are these, and corresponding degree in minimal polynomial is 3 degrees 1, and here it is 2. Now Jordan block, if minimal polynomial has degree 1, we know that Jordan block J lambda with the dimension 2, then that Jordan block means B is of the form lambda 0 lambda, and this is 1, and with the Jordan block with the dimension 1, then it is lambda itself. Now how to get this dimension of Jordan block? So first condition is there must have here Jordan block for lambda equal to 3. Now what is the degree of factor x minus 3 in minimal polynomial? That is equal to 1. So the condition is there must have a block with the same degree as the minimal polynomial. So that is degree is 1, therefore one Jordan block is 3 and other blocks has degree less than or equal to 1. So how many eigenvalues are there? 3, 3, 2. Now other Jordan block must be equal to 3, that is less than or equal. Now second, what about the Jordan block of lambda is equal to 2. Now degree of factor x minus 2 in minimal polynomial is, what is here, 2. So there must have a block of degree 2. So first one is block of dimension 2. So 2, 1, 0, 2 there must have, and other blocks must be, this is the maximum dimension, other block must be, so 2 is maximum. We have how many eigenvalues are there? 4. Therefore other block must be either a block of 2 or 2 is there, then 1 plus 1. So the first is 2 and other block may be 2. And second possibility is there must have a block of degree 2 because dimension of degree of the factor is 2. So this is must. And next is maybe a block with the dimension 1. So the possibility of matrices, Jordan matrices, is first block for lambda is equal to 3, that is 3 must be the eigenvalue 0, 0, 0, 0, and next eigenvalue 3 is a block of degree 1, 0, 0, 0, 0, and next one is other one 2 are 2 is the and block of 1, so 0, 0, 0, 2, 0, 0. So this is a block of 2. Block of 2. And there is 0, 0, 0, 0, 2, 1, 0, 0, 0, 0, 0, 2. So this is, so this matrix is first, and this matrix is in option. This is a matrix Jordan block, and other matrix is 3, 0, 0, 0, 0, and this is 1, and this is always 1 degree, and 0, 0, 2, 1. So there is a matrix of block dimension 2, 0, 0, 0, 0, 0, 2, 0, 0, and other two blocks are of dimension 0, 0, 0, 0, 2, 0, 0, 0, 0, 0, 0, 2. So these blocks are, this is a block of dimension 2